Now let's focus on specific techniques for LLM on explainability. So you have basically two approaches. The local explanation that try to go deeply inside the transformer architecture to understand how to put evidence in some parameter or in the flow. And the other approach is a black box explanation. So from the outside, using techniques of prompting, you try to understand why the model is giving you specific answer, changing specific sentences, omitting specific words, and etc. Basically, the main techniques are around in-context learning and chain of thought. Last, LLM are kind of bullshit. I know it's a hard sentence, but I don't want to spoil more about this, so we'll see what I mean by that.
Thanks again to be here for your attention and time. Thanks to Enrico that already joined you previous year, and it's a pleasure for me to be here. Let's get into things. So, Explainable AI and XAI. All this story started from Enrico that called me about these emerging properties in LLMs. I come from physics, theoretical physics, so hearing about emerging properties triggered me because I was doing theoretical physics, then I started to do code for food, as a lot of us, but theoretical physics was still there. So what is emergence and why we are talking about emergence? Because it seems in some papers that, you talk about emergence when a quantitative changes in a system results in a qualitative change in behavior. This is the definition by Anderson, that is a Nobel Prize. Let's do things practical. What does it mean? In physics, it means that you have a system. At some point, you start seeing behaviors that you cannot predict by basic laws. So think about magnetism, think about symmetry breaking, think about the crystals. All this stuff means that at some point you start seeing things behaving differently and you cannot predict how they are behaving if you just look at fundamental physics. So there is what is called a sort of phase transition, okay? What does it regard to LLMs? What it seems, as you see the nice tree, we trained this machine just to guess the next word in a sentence. And doing this at some point, at some scale, as we say, at some level, number of parameters, they started to provide different behaviors in terms of doing mathematics very well, doing summaries, things that you may not have expected from below, from what you really trained on, doing a probabilistic machine just to guess the next word. And that's where we started, because we thought about XAI. What is XAI? In general, machine learning produces models that are pretty opaque. XAI is used in order to study these machine learning models. We will talk more about it. But we tried to couple this, trying to understand this behavior, looking as a black box to these LLMs. Consider one thing that, I liked it a lot. 20 years ago, maybe, we were convinced that we needed to model the word and model the language. So two different aspects in order to do general AI or whatever else. Now it seems that just having a language model is enough. Like syntax is enough. You do not need the semantic. You do not need to transfer a model of the word. Model of the word will emerge automatically. This is pretty at the interface between, physics. The irony is that the two Nobel Prizes this year of physics are indeed machine learning. So physics, philosophy, kind of interesting and intriguing questions. So let's go ahead. Let's touch with hands what are these emerging properties. As I said, an ability is emergent if it is not present in smaller model, but present in larger model, phase transition. Look at right. what you see is clear evidence in literature about this emerging behavior in LLMs. You see there is a kind of threshold, the random, the random behavior when you are not seeing nothing special in this specific task that is arithmetic, word unscramble, specific task. Then at some point you see a discontinuity. What happens is that if you read on the x-axis, you see the number of parameters. At some point, a new behavior emerges. This has been intensively studied, and there is no conclusion on this stuff, in the sense that we are providing this evidence, but let's look also the other way around. There are a lot of dubs, still a lot of dubs of being real emerging properties. Why? What it seems is that, in the middle, you see the normal, the standard graphs, loss function and probability. They are pretty nice function, pretty linear and smooth. Now you see the two, let's say, the two angles on which you can look at two different things, emergent abilities or not emergent abilities. If you use some specific metrics that are intrinsically discontinuous, like multi-choice grade, in which you get all or nothing in the multi-choice grade, or you get kind of the accuracy, the standard accuracy, then you have the diagrams on the left. Emerging properties are there. So, what's happening? LLMs are providing new behaviors, very good. So we need to increase a lot the parameters. We will see the singularity. We will see what else. But if you change the metrics and you start to use error per token or kind of more continuous and intrinsic metric, you see that emerging behavior may disappear. The diagram, the function, get smoother and smoother. You do not see the phase transition. So I do not have an answer, but I think it's very interesting, okay? This is the context. Let's turn to the other main role on this. I always like to introduce XAI with this story. It was 2016. There is a nice movie on Netflix about this. A lot of hype because the champions, the Go champions, was defeated by AlphaGo, like happened on chess. Here we are interested on a specific thing that happened there. The fact that when the artificial system got the 37th move that was crucial to win the game, what was said is that by another Go champion, this is not a human move. Also seeing at the move after the end of the game, this would not have been played by any human player. This is important. I use this to introduce XAI. Machine learning models are opaque, as I said. In this case, you cannot predict this move because something emerged, but you cannot explain even though you look at the game at the end. So some pattern has been recognized, but you cannot ask why did you play that move, okay? Let's go more practical. So XAI used the techniques, also nothing new in science. XAI means to study a black box. In this case, the black box is a machine learning model. You see a lot of nice examples. You can see machine learning models that are very, very accurate on predicting, recognizing wolves. But then you discover with XAI that they are just looking at snow. There is bias on the data, okay? But you may not know that to predict, to say this is a wolf, it is just looking maybe at snow or maybe at the photographer that introduces a pixel to sign each photo, and this man just takes picture of wolves, okay? This is very bad. Also to trust the system. But even more fun is the fact how a guitar is recognized. We would hope that the machine learning models will recognize things as we do. So looking at the robust features of a guitar, while you can see that also the image near the guitar is recognized as a guitar, even though the pattern that is used, it's not very useful to say this is a guitar, okay? This opens also another streams between XAI and security, because you know better than me about one pixel attacks. You can fool the machine learning models. All these topics are summarized in these 4 bullets that tell us about XAI. XAI is important, first of all, because call it GDPR or whatever else, but as humans, we are entitled to ask, why did I get this answer from you? Why did you get this choice? Okay, I need to know. I'm entitled to know why, which are the criteria to get the low one or not, to get the diagnosis or not. So, first of all. Second, as I was mentioning, XAI is coupled with robustness of the machine learning model. What you may learn is that the more robust is the model in terms of features that cannot be perturbed, the more you can explain the model. Fairness is obvious. You may recognize fairness just after, just looking through XAI techniques. Last but not least, this is very important for our LLMs. You know, science now is increasing the usage of machine learning to do knowledge discovery. Knowledge discovery is something different from just getting accuracy and prediction. We want to understand why, how a system is built, how the system behaves. Now, also in this case, it's not simple to have real knowledge discovery with this object that could be very, very accurate, but could not have a solid representation of the system. As I said, now we are just getting a language model that works very well, but maybe there is no knowledge about the word model, okay? So what I want to do now is to quickly pass through XAI techniques before handing over to Enrico that will use these techniques to say something more about these LLMs. Remember that they are just guessing the next word, but we will talk it more and more later. Standard XAI taxonomy. We have the model interpretability, and you have 2 main families of techniques. The post hoc, that means you just do it after the model has been built, so they could be agnostic to the model or specific to the model in the sense that the technique requires the fact that you know specifically that model. The more simple one are the other family, the intrinsic explainable model. Think about decision tree or linear regression. You do not need any XAI to understand why there is a classification or why there is a result. But let's start simple. So in an intrinsic explainable model, you have a linear model, you have the coefficients. So no need of XAI, you just read the coefficient. Just pay attention to the fact you know for sure correlation is not causation. You know, there are a lot of ice creams that are sold and there are a lot of drowning men, but ice creams are not causing the fact that a lot of people are dying in the sea. It's just summer, okay? But a lot of times this could happen, okay? The first and most simple but powerful XAI method is the permutation importance. You have whatever model, this is agnostic, you just shuffle the values in a feature and you see if the prediction change. This, for sure, will assure you if this feature is important or not of the model, because you are scrambling the data and see what happens. So very, very intuitive, but this is the meaning of XAI. You do not know the model, you want to see how it is predicting what is predicting. Another example around the same, man of the match, number of goals scored through permutation importance. I use this because you can do one step further, that is partial dependent plot. You can see the functional relation between the feature and the outcome. So you see here that the goal scores are important, but at some point it doesn't matter. And you can see that the kilometers you are doing in the field have some different behavior, not just linear. The important point is that you can mix the feature and see in some specific region of the parameters what is really triggering the behavior of the model to predict something instead of something else. A great family of agnostic methods like LLM and others work on the concept of global surrogate, and we will see this more also in LLMs. What means global surrogate? You have a very complex model in which, deep neural network or whatever else, What you do, again, is what you would do in other fields of science. You do an approximation of the model near a point or in general with a linear model. So you use the data, the synthetic data coming from the model you want to study to train a surrogate that is linear, that is easy to explain, and you use it up to some extent, as when you do Taylor expansion or something like that. You just use a straight line instead of a curve. You can explain a straight line or the plane, and you do prediction near the point in which this approximation could be useful or not. SHAP is very, very used. I mentioned this because we will see the limits in LLMs of this approach. This comes from game theory. This means that here each feature is a kind of player in a cooperative game, and each feature can shift the prediction on each specific point. Consider that the other two subfamilies are local explanation vs global explanation. You may be interested on a specific point that has been predicted, or globally. This is for local explanation. And this diagram is very useful because in one diagram you can see a lot of information. How much the feature is important, how much is shifting the value of the prediction. So SHAP is a very, very powerful technique. And now we are approaching more and more the world of large language models. Here you see occlusion maps. They are used both during training, if you want your model to be really robust, recognizing things from important feature and not just details. You can use it the other way around. After you had trained, you start to use a patch to hide some parts of the image in this case and see what the machine learning model is really looking at in order to get that prediction. Here you see the photo, but let's say a bit of spoiler. Imagine that instead of an image, you have a text, and you start to scramble the words and see how the LLMs behaves. You can see how much is robust and how much is important for the LLM to use one word instead of the other, okay? But Enrico will make you touch with hands this part. Grad-Cam is a variation. Here you need to know the gradients on the convolutional layers, but it's very, very powerful in order to understand more and more about how an image is recognized based on the last level of the convolutional level. This is just an example from my work. We are doing phishing training. We are interested on understanding why do you click something and not something else. The old approach was, okay, I will craft a very good phishing email because you are an IT geek, I will send you something that is about IT. What is emerging with machine learning is that machine learning is capable to make you click with features that are not obvious. Maybe you click everything I sent you at 7 o'clock in the morning. As a human, I would not expect, but the data say that. It would be also interesting to understand this feature as an emerging characteristics of what makes the people to click or not, in addition on the fact that I sent you a very, very specific mail for you or something like that. And that's, this is a review of XAI. So let me do kind of quick summary before passing the microphone to Enrico. So emerging properties, something that is very clear in physics, now is used in LLMs because it seems their behaviors cannot be predicted from the basics. I just trained them to guess the next word, and now they are doing as a physics PhD on problems, okay? This is not expected. These are emerging properties, we do not know. Maybe depends on the metrics that I use to measure this kind of behavior. Then what we want to do is to use XAI to look into these objects. XAI is an old technique, pretty old, but very, very important, because unless you really think about XAI, consider that you may not be able to really scale with this machine learning in critical application, healthcare, finance. If you cannot answer the question, why did I get this prediction? Why did you say that? I cannot do solid machine learning. So, could I use XAI for LLMs? I showed some techniques. The bad news is that they cannot be easily adapted to LLMs because they are really, really complex. We know that in terms of number of parameters. So the usual approach, SHAP or whatever else, do not scale so easily at LLMs level. Obviously, we will try to do similar approach, and you see on the right a kind of taxonomy that groups the XAI techniques for LLMs based on the paradigm, fine-tuning, prompt, and try to do something. But this is still an open, an open stream of research that Enrico will try to clarify as much as we can. Thank you.
Okay, so let's try to deep dive into the large language model, try to apply these techniques about explainable AI. So, first of all, just a definition, everyone knows, but just to use the same terminology. So large language models are basically giant neural networks with billions of parameters, trained on large quantities of unlabelable text using self-supervised learning. So that's the definition. How they works, they split the message into tokens and they translate this token into numbers because, as we know, the neural networks just digest numbers. And at the end, they do the vice versa. They translate the numbers into tokens. But what they did is just literally guessing the next token into a sentence. That's it. So that's how they works. And this is called appendix, by the way, when you translate a message into numbers. So everything's changed in 2017 with this paper. Attention is all you need. A paper came from University of Toronto and Google, actually more Google than University of Toronto. So it's the first time that this architecture appeared, is the transformer architecture, and this changed everything. So basically after this article, all the natural language processing techniques almost disappear because everyone now is using LLM to do natural language processing. It's very nice, this architecture, because of scale. Of course, coming from Google, they propose something that scale, because in the theory about NLM, we had also RNNN. There was similar architecture, but didn't scale, because there was a back propagation system, so you cannot scale. So this architecture scales, and using GPU, now everyone can run LLM on a laptop, basically. Behind the transformer, this is quite complex idea, there is the attention map. So this is the key point of this architecture. So basically, when we have a sentence, you get to the LLM. The LLM is trying to combine all the possible combination of the tokens and try to understand the weight that the token is related to each other. So internally, something like this is coming. So if you get the sentence, the teacher taught the students with a book, this is what basically the LLM does, try to match all the words. I'm simplifying here, I'm not talking about token, just words. So teacher, student, and book are the evidence from a semantic point of view that emerge using this neural network. And this is called attention map. This is a nice example, in my opinion, because if you think about in English, the teacher taught the student with the book, it's a kind of not really clear sentence. What means that the student teach only with the students with the book, or the teacher used the book to teach to the students, or both. You know, language is complicated, right? So it's quite amazing that we built a system that is able to giving the meaning, all the possible meaning from a sentence. That's why the idea of attention map came up, because you have to take in care all the possible combination. The transformer architecture is very complex, so I don't want to explain. This is not the moment to explain, but just to give you the flow, the flavor of the architecture. So we have input and output. Input is in the bottom, output is in the top, and we have an encoder and decoder phase. More or less, the encoder get the point where you have the sentences and try to match the self-attention of the sentences. And the coder is putting, again, another self-attention, but in the sensor itself. So as you can see, there is a loop. That means the output is given back to the input as a feedback, and that's how the model works. So it's just try to predict the next word, and if you can think that this is a probabilistic machine, the fact that I pick a word and for the next token can give you a completely different, output. This is why they call it the generative system, because they literally can generate different sentences just picking up a different word in the procedure. How they pick up? Almost randomly, in the sense that at the end, and I will show you an example, at the end of this architecture, you have a list of probability and words, and they just pick up, for instance, using the top key algorithm. Imagine you have the three top response. You can actually pick up one of these randomly. And actually, this is the best way to generate text that looks like human, because that's one of the big points of this presentation. There is no semantic inside LLM. There is not meaning inside LLM. One of very interesting, if you are a software engineer, I think this is the most important parameter about LLM, is the temperature. You can actually change the distribution of probability of the next token. And that means this is basically a floating point parameter. If it's 0, you will get always the most probable token from the output. If it's greater than 0, you basically change the distribution. That means you can pick up different and generate more creative response. So my suggestion, if you need to do something almost deterministic, use temperature 0. For instance, if you are generating code, LLM model to generate code in computer languages, it's always better to use 0. If you need to write a sentence or asking to rewrite a sentence or do summarization, whatever, you can increase the temperature. Okay, so now let's focus on specific techniques for LLM on explainability. Of course, in 20 minutes, it's almost impossible to give you all the actual, articles about these topics. So I pick up, in our opinion, the most significant one. So you have basically two approaches. The local explanation that try to go deeply inside the transformer architecture to understand how to put evidence in some parameter or in the flow. And we have visualization attention, the heat map of self-attention, the transformer explainer, the LLM visualization. These are just tools that I will show briefly. And the other approach is a black box explanation. So from the outside, using techniques of prompting, you try to understand why the model is giving you specific answer, changing specific sentences, omitting the specific words, and etc. And basically, the main techniques are around in-context learning and chain of thought. So these are the two techniques. There are a lot of benchmarks proposed on this. I will show you just one, that is GSM-Symbolic benchmark. And last, LLM are kind of bullshit. I know it's a very hard sentence, but I don't want to spoiler more about this. So we'll see what I mean by that. There is a very nice article appeared recently, actually in October of this year, where basically the author of this article did a survey on all the possible XAI techniques applied to the LLM. So if are you curious, I strongly suggest to have a look at this paper, because it's a very, very good summary. In this table, you can see all the possible techniques, so the paper, and in the last column, you have the goal. So they divided into comparison of model, explanation, improvement, interoperability, reasoning, and etc. So I think it's very, very, if you are interested in these topics, this is the article to start. Okay, let's focus on the first idea. So try to visualize the attention mechanisms inside the transformer. So this is kind of a visual techniques. This is an open source tool that basically give you the possibility to understand on different layers, because again, we are talking about a neural network here, so based by multiple layers. For each layer, how the weights between the words are connected to each other using this graphical representation. Again, this is an open source project, so there is the GitHub repository with all the paper, of course, but also with the Colab tutorial. So I think this is very nice because you can literally run the code on Google Colab. Of course, it's Python code, and have a look at the introspection about the model. So I think this is very, very nice way to try to understand what's going on inside the transformer architecture. Another techniques is the heat map. Also, Leonida showed some example before. So this is just a couple of lines of Python code. There is this library, insec, very nice. As you can see, I'm just getting a specific model here. Is one of translating English to French, so very specific example here. You instantiate the model, you give a prompt. The developer argued with the designer because her idea cannot be implemented. And you can literally see how internally the model is running and giving the heat map of the self-attention. Here there is an example. So this is the outcome of the out.show. So you can literally see inside, like if you want to do a comparison between software engineering and LLM, this is kind of a debug of monitoring the system inside to try to understand what's going on. One very nice tool is the Transformer Explainer, very famous in the field. Again, it's an open source project where literally you can explore the inside of the transformer architecture. In top, you can see the sentence, and when you go in a specific words, you can have all the possible combination using a visual representation. Of course, it's a lot of information, but at least this is a nice way to try to understand what's going on. This is, I would say, the classic explainability approach. We have other example, always open source. This is kind of the same visualization system. You can have, this is the transformer architecture on the left, and you can see that each time we go inside a specific layer, the diagram is showing you the specific, part that are triggered. And again, I think it's very nice. Of course, this is running in your browser, so you cannot expect to run, big models unless you have a big machine for testing. And also the transformer that I showed you earlier, from a software engineer point of view, is very nice because basically the LLM is running into the browser using a WebAssembly. So it's even interesting if you are not just a software engineer, you want to have a look at the internal details. Okay, so last way to, very similar also to the example that Leonida did before, is an attempt to understand the large vision language models. So this is called also multimodal large language model. So basically models that are able to understand images. So you can literally put an images to the LLM asking for, give me the description of this image. Or the opposite, you can create images using text. So this kind of model, and we have recently Llama 3.2, Llama 3.3 that are also multimodal if you want to use the open source model. In this article, they find out using explainability techniques that basically these LLM are able to understand the images just using the first layer. So using only the shallow layers. As you can see in the image, we have the original in the picture. We have in the first column the images. The second column is the layer 2, layer 6, layer 12, and so on. As you can see, when you go deeply inside the layers, basically the model is not getting information. So this is nice because it's an example of how to optimize this kind of tools, because LLM are, very brute force approach to the problem. So now in the literature, we are seeing people trying to optimize the transformer architecture. So in this example, we can literally reduce a lot the execution because we can remove the hidden layer, basically, if we are working on images. And this is called the Grad-Cam visualization. So this is a specific framework that they basically use it. Okay, so now let's try to show an example, not going inside the algorithm, inside the transformer architecture, but outside. So let's try to understand how the LLM works from the outside as a black box machine. And they propose that in literature a lot of benchmark. One of the recent is this GSM-Symbolic. So basically, it's a way to measure the reasoning capabilities of large language model. How they do that? So basically, they use, in-context learning to try to solve a mathematical problem. So very simple mathematical problems, and they try to change in a techniques very similar to the one that Leonida mentioned. Change just the input, shuffling the numbers, changing the numbers to, I don't know, positive to negative, integer to floating point, a very basic, substitution of numbers. And the LLM that they tested, they didn't have the same behavior. So if you change just the number, you confuse the LLM. So the answer was not really useful and correct. So the conclusion of this article was that basically LLM are not capable of genuine logical reasoning. So at least not as a human behave, right? So it seems that these models are not capable to abstract the resolution of a problem. They are only able to follow the fine-tuning, so the example that you give, because if you change a little bit the example or the context, for instance, with the numbers, the model basically is not capable to give you a correct answer. So they are very fragile in this regard. So this, I think, is a very important point that Explainable AI give us about the large language model. Last example that I want to mention, I know it's a hard sentence in English. This is the title of the article, ChatGPT is bullshit, in the sense of the philosopher Frankfurt. He wrote a book about that on bullshit, philosopher of Princeton, 2005. So basically, the idea is that the model are an important way indifferent to the truth of their output. So as I mentioned earlier, LLM doesn't know about if a sentence is true or not. They only complete sentences. So we cannot trust this model because the model itself doesn't know. And this is typical of what bullshit does. So typically when you say something about bullshit, you refer to a person that is just talking without any evidence, any experience, any knowledge about the true or false. It's just chatting. We have a similar word in Italian, but I'm not going to tell you. You can find out. So I think it's important, even if, of course, this is kind of provocation, title, talking about bullshit. But I think it's important because if we think that we are using a model that doesn't know about the answer, it's a kind of bullshit, I think we can design and use this model better. So that's the point of this article. It's not saying that this model are bullshit, so you cannot use it. You can use it, of course. There are amazing technology, but you cannot trust, so you cannot literally ask to a model to explain why they give you an answer. So this is very, very important. Unless you ask to specific topics where the LLM has trained by. But even if you change some input, you can get unexpected behavior. So you cannot trust. Of course, this model are probabilistic model. So in 99% of the case, you get a pretty good answer. But if you try to, use different techniques like, I don't know, prompt injection, and I think there is also a talk about these topics in this conference. So I suggest to, listen about this, because there are a lot of ways to work around a prompt and giving, different behavior. So the conclusion are, of course, LLM are very nice technology, and they give you, they basically gave us an incredible leap to natural language processing. It seems that there are emergent properties in this large language model, as Leonida also said, like, for instance, mathematical problems. Traditional XAI techniques are not able to literally, discover or understand what's going on inside this model. So we have basically a limited knowledge about these emergent properties in a large language model. Recent studies have, tried to perceive the reasoning of this, the capabilities of this large language model, and how this emergent problem came in the LLM is still an open question. The perceived reasoning from the attention mechanisms is still under study. So we give some references. Again, this is a very huge topics. I hope me and Leonida give you at least an introduction. So thank you very much.
Okay, thank you, Enrico, Leonida, for that deep dive.
Very, very good, very interesting. Now it's time to grab some coffee.